All right, my friends, the final section in chapter 5 is 5.7, the word problem section. It's officially called Quadratic and Linear Functions as Mathematical Models, but the main focus is their word problems, basically. They're going to throw a few linears in there just to keep it exciting, but we're focused mostly on the quadratic. So these are things in the real world that don't act in a straight line fashion, like, for instance, a soccer ball that was kicked. You'll learn in physics, if you haven't already, that stuff that's flying through the air without a motor moves in a parabolic fashion in the world with no air, of course. You'll ask your science teachers about that. But stuff that's just flying moves in a parabola. I've also decided that I'm tired of looking at the red, and you pretty much write down everything anyway, so I don't need to distinguish between writing in red and not. So we're going blue today. So here's the main two, or these are two types of setups. I'm just going to get these parabolas set up and then trust that you can work with that equation by plugging in x's and getting y's, or plugging in y's or getting x's, or finding the vertex, or whatever questions they might ask you. You've already learned all of those skills. I'm just trying to come up with the equation. So in this first one, the soccer ball is kicked. When it was kicked, it was 4 feet above the ground. 1 second later, it was 28 feet high, and 2 seconds later, it was 20 feet high. So we've got two variables here. The question, which I didn't put into words, is write a function for the height of the ball x seconds after it was kicked. And just to practice using letters other than x and y, let's let t equal time, or seconds since the kick, and let's let h equal height of the ball. Now, whenever one of your variables is time, time goes on, it doesn't depend on anything. So time is always going to be your x. So we're going to form three data points based on our statement. The first statement is that when it was kicked, it was 4 feet above the ground. So the actual foot hit the ball when the ball was 4 feet above the ground. So 0 seconds into this process, the ball has a height of 4. 1 second later, it's at 28, and 2 seconds later, it is definitely on the way down at 20. I'm assuming, I'm not sure if the 128, if that was past the peak or short of the peak. We'll see when we get to a picture. But in the last section, we learned how to take three data points like this and make them into the equation of a parabola. So back to the calculator. The easy way to do this is in stat. Go away now. Oh, no. Excuse me. Don't need you. Please work, calculator. There it is, stat. And I've got my old x's and y's back in there. If you go up and highlight L1 and hit clear, come back down, it'll clear it out for you. So in this case, my x's are 0 seconds, 1 second, and 2 seconds. And my y's are 4 feet and 28 feet and 20 feet. And remember, the quick way to do this is go back to stat, go over to calc, quadratic regression, 5. And you don't even have to hit L1, L2. It's programmed to do L1, L2. And here's my formula. Here's my function. Negative 16x squared plus 40x plus 4. Negative 16, 40, and 4. So my equation is h of t, height in terms of time, equals negative 16 t squared plus 40t plus 4. And you should notice right away that that 4 is going to end up being our y-intercept when t is 0. I guess it's our h-intercept. And you can tell that because when t is 0, h ends up being 4. All right, so I'm going to also, let me show you one other thing here. If you do that stat, oh no, here's my ink again. Stat, calc, option 5. Before you hit enter, if you hit vars which is right there. Then go to the right, then hit enter on function, then hit enter on y1, and then hit enter one more time. That will not only find the equation for you, but it will store the equation in y1. You can see on my other screen over here, it put it in y1. If you just go to y1, you'll see it in there. So that saves you the time of having to type it in. And now if I go to graph, I have a feeling like my picture is not going to be great because my standard zoom is from -10 to 10 in both directions. So on my window, X is my time. I'm going to go -1 just to give my picture a little bit of breathing room on the left. And then let's see, I'm going to go max, I don't know how many seconds. From my first graph, I can tell this motion is not going to last more than 4 or 5 seconds. So I'll go up to 5. No, not there. I'm going to go -1 to 5. And that X scale is just counting by ones. That doesn't mean much. My Y minimum, Y is my height. So I'm going to go -1 again. I really need to start at 0, but I'm just going to give myself a little room. And I know my ball reached 28 feet, so I'm going to go up to 35 feet, and hopefully that will cover it. So change that window and go back to graph, and there you go. There's the motion of the ball. Right over here on the intercept, it crosses at 4. It looks like it stays in the air for a little bit more than 2.5 seconds. So with that in the calculator, you can do all sorts of stuff. But again, this video's focus is just to get the equation. But I wanted to show you how to get it into y equals while you're at it. Okay, so another way you can get a quadratic is kind of with a geometric version. Sometimes this will be like a pool with a path going around it. In this case, it's a picture, 11 by 14 inch picture that's going to get framed. So let's see, let me draw my picture. Here's my 11 by 14 picture, and then I'm going to frame the guy. So here's the frame. And this frame has a width of x. So this is 11. This is 14. And this is x. And what I need is a function for the entire area of the framed picture in terms of x. And you can see that if x increases, the area is going to go up. So it does depend on the width of the frame. And just as a preview to future things, this is the area is in 2 dimensions, and the x is in 1 dimension. And if you increase your area by 1 dimension, you'll increase your area, you increase your length in 1 dimension, you're going to increase your area in 2 dimensions, and that's why it ends up being quadratic. Probably shouldn't get too far into that today. Anyway, the total height of this picture from here to here, once it's framed, is going to be 14 plus 2x, because I've got a width on the top and a width on the bottom of the x. And then side to side, I'm going to get 11 plus 2x. So the entire area of this framed picture, a of x, is going to be length times width. So 11 plus 2x times 14 plus 2x. And you can see how when we FOIL this, we're going to end up with a quadratic, hopefully. All right, so 11 times 14 is, 4, 4, 0, 1, 1, 154. Should have been able to do that in my head. I'm not that good at math. 154 plus 22x plus 28x plus 4x squared. So I'm going to put that back into the right order. 4x squared plus, see, 22 and 28, that's 50x plus 154. Okay? So notice that 154, where do you think that is in this whole scenario? That's 14 times 11, right? So in here, we've got 154. And then we've got 50x. I wonder where that came from. What about these 4 rectangles right here? Interesting. Let me see. What do we got here? 11x right there. 14x. That makes 25x. and 11 more and 14 more. Oh, there's 50x right there. And then 4x squared. How big is that rectangle right there? X squared. 2, 3, 4x squared. Cool. Okay, so that little drawing, I noticed that and it was fun. But the point is that we have created a quadratic equation from a description. And we could use that equation to say, well, what if the frame were 2 inches wide? How big would the picture be? What if the frame were 3 inches wide? How big would the whole thing be? Or I have this many square inches on my wall. How big a frame can I use and still make it fit? That would be predicting an x based on a y. We can use those and have all sorts of fun with them, but for now, just coming up with the equations is what I need you to worry about. So most of them will be like our first example, where you take 3 data points, plug them in your calculator, and get the function, and then use it. But occasionally, you'll get one like this, where you have to use some geometry and come up the equation that way. And like I said earlier, they'll throw some linears into this section just to keep you on your toes. All right, but we have reached the end of the chapter. Let's see. Thursday of this week was sections 5 and 6. So we'll talk about this in class Friday, and we will review on Monday, and our next test should be on Tuesday. And I'll confirm that schedule with you in class, but that's looking like it's going to be that way. All right, so have a good one. I will see you in class, young out.